So let's talk about password hashes. Um, Passwords used to be stored in plain text on machines like MS-DOS, but for decades they aren't stored that way. They're stored in hashed forms. Microsoft uses an incredibly weak algorithm to store password hashes that is 1,000,000 times weaker than the one used by Linux, and that's where we're going to start. So if you go to a Windows machine and create an account with a password and then harvest the hash with a hacking tool like Kane, or there are many others, then here's the actual hash of that password. And because Microsoft does not salt passwords, if two users have the same password, they have exactly the same password hash. So by the way, if you want to crack a Windows password hash, all you have to do is Google it. Because for 30 years, everybody's been building dictionaries of Windows password hashes, and any fairly common password will be found just by a Google search. So this is password, of course, but you can try almost anything. Unless the password is fairly unique, you'll find it with nothing more than a Google search because of the Microsoft neglecting most of the important security features in password hashes. So let's try and calculate these. These are Microsoft Windows hashes, and they were invented in 1993 to come out with Windows NT version 1, or whatever it was, the first version that came out. And at that time, MD5 had not yet been written. The most advanced algorithm available at that time was MD4, and Microsoft never updated their stuff after 1993. So they're still using MD4. So if I wanted to hash the word password, I would take the string password, encode it to turn it into bytes, and hash it with MD4, and this is just how you use the hash lib that you can import. I make a new hash object of algorithm MD4, and this is the input data. And then the object itself is just an object with several attributes and methods, and the method hex digest is what turns it into just a readable string of hex characters. So that should do it. Python 3. Whoa, got to spell Python better. Hash 1. All right, so it gives me a hex output of a hash value, but it's wrong. The correct value is 8846, and this is 8AD9. It's wrong. And the reason it's wrong is because even in 1993, Microsoft was not content to be English only. They wanted to sell it in Europe and Asia and Africa and everywhere, so it was an international language. Now, it would have been nice if they could use the kind of Unicode we talked about earlier, UTF-8, but I think that was also not available at that time. Instead, they used a really old kind of Unicode, which is called UTF-16LE. And this is a very strange version of Unicode that uses 16 bits per character, so that even normal ASCII characters have an extra byte of 0 after each one, so it is like the worst of all worlds. Normal ASCII is changed to be incompatible and made longer to waste half the storage, and you don't have enough bits to really encode all the international characters you need to encode. So this was an early version of Unicode that wasn't very good and later turned into the later versions of Unicode, which are better. But that's what Microsoft uses. That's what Windows uses on almost all strings in Windows software and the Windows operating system, is this old 16-bit Unicode. So to do that, you have to use this, hash 2. And that's what it does. When you encode it, instead of just saying encode, which will encode it as ASCII, you have to tell it to encode it as this specific version of Unicode with 16 bits per character. And then you'll get the right value. Python 3 hash 2. Now I get the 8846, which is the correct value. So now I can create Microsoft password hashes, the kind that are stored on the disk in the SAM file in the registry. So the first thing you do is make a dictionary that calculates all the hashes for 2-digit passwords, 00 through 99. And there's a flag defined in there. Then I made a format where you have 3 users, Ming, Mohammed, and Sam. And you put the name here, CCSF dash, the name dash, and then a 2-digit number. So there's really only 100 possibilities for the password, because the only thing that changes is the 2 digits at the end. So here's some passwords to crack. Now I got these from Windows 7 machine with Kane. So this is the way Microsoft password hashes look. It has the name of the user, then some other field that's blank. Then it has the old LM hash, which is always this dummy value, because that's so old even Microsoft won't use it anymore. And this is there just for compatibility. This is the actual NT hash, which is what you've created with this MD4 stuff. So you'll have to create your hashes here and find the one that matches this part of the value over here. And of course, you can see a few problems like this is lowercase and that's uppercase and so on. And now you'll have a list of 100 you have to look through. There are various ways to do that. You can program it to match it. You can be incredibly sleazy like I often am and just output it into a file and then use a word processor to look for the string. There's many solutions. I say many students write much more elegant, beautiful programs than I do. I changed my attitude about that when I worked in the financial sector. My boss said, what you have to do is make sure it's right every time. And I couldn't care less whether it's elegant. So I always used very simple brute force solutions like hitting it with a hammer. Anyway, then you got one here where you have several rounds of MD5. So you hash it with MD5 and then you hash the hash. And then you hash the hash again, up to 100 rounds. And you're going to crack some passwords and you don't even know how many rounds. So you'll have to calculate a lot of hashes. And what you'll discover is what's wrong with Microsoft hashes. This is not hard at all. You can calculate these hashes very, very fast. They're designed to be fast. So even though you want to do up to 100 rounds and 100 possible passwords, so that's 10,000, and 3 users, that's 30,000, that's nothing. That's like 1 second of processing time. And down here you have many rounds of MD5 followed by many rounds of SHA-1, and you'll still have no trouble cracking it, which is why Linux password hashes are salted and stretched. They add random characters to them so that each one is different, and then they stretch them by doing 5,000 rounds of SHA-512 to actually spend so much time computing that a bad guy cannot try a database of millions of passwords. You'll find you can only try hundreds of passwords in a reasonable amount of time, which makes your passwords much safer. And that's what we have down here. Here's the Linux password hashes, and here's how to calculate them. And this is the next to most modern technique. Colley's now moved to the one after this, but this is type 6, where you have a salt that's, I think, 16 random characters, up to where the dollars is. This is random characters added to the password. Then it's hashed with 5,000 rounds of SHA-512, and that's what this mesh is. So those you can crack. Again, I'm only giving you 100 options to hunt through, so it's not too bad, but you'll find that this actually takes some time to compute, and that's the point of it. And then there's LastPass hashes. LastPass says they use a random salt and 100,000 rounds of SHA-256. So I did that, and here are some of those passwords hashed with that format. And I always used the same value for the salt here, which is not a best practice, but it's a way to go. And this is all the hash now. The hash is getting pretty long with SHA-256. So anyway, there's some password hash solutions, challenges to do with Python.